So the basic introduction is that you all should have a VM either downloaded or we sent out the thumb drives. So whoever needs, you can upgrade your VM. So just in case, so everyone has VirtualBox on their machines. So that's virtual appliance that you just need to import. To use that VM, especially to use a sudo command, you need to know that the password is the same as the username. It's Ubuntu. So that's how you use it. I don't know if you don't have a lot of experience with VirtualBox. One thing which would be real, it should work pretty much like a real system, but it would be, you'll enjoy it more if you install what's called the VirtualBox additions. And so in there's a menu, you just say devices, insert guest additional CD image, and then it will kind of do the work for you. So then you can, you know, for example, change the window size and all those kind of nice things. So that's kind of the very basics, but that's not the interesting part. The interesting part is how this whole thing works. And so that's where we'll see, because it's also a very practical way showing how in general P4 is going to work on a real system. Okay? So we will all start obviously our programming by writing the code. So imagine that you have written a program called test.p4. So there is a compiler there which can compile this program, and it's called P4CBMD2. And so it can compile this program for the behavioral model version 2. And so the output of this compiler is a file called test.json. You can provide any name, but I think it's nicer. It has the same name, just a different extension compared to the original source file. So think of it as your object code. So then the other part, which is super duper important, is BM, behavioral model version 2. So what this behavioral model is really consists of several important parts. So this is really the model itself. So it has some abstract port interface, which allows us to get packets in and out. Once the packets go in, they go through the parser, ingress pipeline. Then there is a certain model of the traffic manager, which allows us to do queuing replication. Then the packets go through the ingress pipeline, the parser, and out of the port interface. So initially this model, as a real pizza chip, it does not know anything about any protocols. So what we'll have to do when we start the model, we'll specify the compiled file, that same test.json. And so the model, it goes in here, and I try to draw it like as if it's a SIM card on your phone, right? Then it gives you the personality. And so then the model will start operating the way you want it to operate. Now, the question that we always tend to kind of avoid is what the control path does. And typically the answer is like P4 has nothing to do with control path, right? But it is super duper important that we all understand that ultimately without control path nothing happens. And so I think the biggest thing, next thing in P4 will also be the ability to more formally define the control path. So how the control path is supposed to talk to an entity which runs a P4 program. So what we have here is the model just opens a socket, which understands thrift messages. Everyone knows approximately what thrift is. Just a nice RPC framework. And so there is a protocol defined by the model, and I'll talk a little bit about it. It's a very simple protocol which allows us to program the tables, retrieve the counters, set the meters, and so on and so forth, so that we can actually program the switch exactly as we want. So to do all that, there is a generic CLI program which can talk this using this protocol. Now, you think about that, how do you define, how do you design that control path to P4? Remember, all I was drawing for you were pretty much those rectangular pieces of stuff called tables, right? And think about maybe another language which is really suitable to manipulate tables like C, right? So what do? You can add an entry to the table, right? So you need to specify the key, maybe the priority, the action, and the action data, right? You can delete the entry from a table. You can modify the entry. If you have a counter, the name of the counter array and the index, you should be able to get the counter. So the operations are very, very generic. But for a given table, you need to know exactly which fields constitute the key, what are the actions, and so on. So this CLI uses this generic protocol to talk, but in order to be able to pass the correct table numbers and so on, it also needs the space.json file to be passed to it. So then it can actually operate on the tables which are in this device. So right now, I think it's possible to mix, and then of course your results will be unpredictable. So make sure that when you start the model and you start the CLI, you use the same JSON. And also very, very important, especially for the debugging, you need to be able to log the events. And the nice thing is that the DMV2 has a very, very systematic formalized logging, so you can see all the tables that the packet passes through, everything that happens to it and so forth. So it can go to the console, and that's the default that we'll use. Or actually the nice thing is there is another way to do it. So it can be another message bus, and then you can start a separate process, the logger. And again, the messages are very, very generic. So for the logger to be able to decode those messages, you'll also need to plug in the compiled program. So everything is totally generic, and it is the compiled program in the form of a JSON file that provides the personnel to that software. And last but not least, to interface with the ports, they actually we bind them to the Linux network interfaces that exist in the kernel. They could be real physical interfaces, but because your laptops don't have that many, we actually create virtual interfaces and bind them to the virtual interfaces. That's kind of the most practical thing. And once this happens, then you can have a separate program, which is packet generator. It can inject the packet into one of the interfaces, and you can have a packet sniffer, which gets the packets out. Okay? So that's kind of the overall structure. So you see there are lots of pieces. Very often when people work with that, they open like 1, 2, 3, 4, or sometimes 5 if they want to do it separately, console windows to make it sort of easy and understandable to us. So how do you call this stuff? It's actually fairly simple. So if you want to compile the program, you just say p4cbmv2, use --JSON, pass the number of the name of the output file, and that compiles your program. So that's like super duper trivial, but you can have it as a reference. Then what we need to do, we need to create those virtual interfaces in the Linux kernel. And so what we do is, because we create these, there's a script that is also available inside the files that we gave you in the tutorial directory called vsetup. It's crucial that you execute it through as a super user. Otherwise, Linux will not allow you to do that kind of stuff. And so what it does, it creates pairs of virtual Ethernet interfaces that are connected to each other. So even are connected to odd. So here I'm going to put for, as a reference how we do that. But the essence is that when you do like IP link add, and you specify two names like buf0 and buf1, and you say it's a pair, that's what creates a pair of those connected through a virtual link. And then the other crucial thing that we need to do, unfortunately, is that we need to like make sure that Linux stack does not do anything unexpected on those interfaces. So for example, we have to disable IPv6, otherwise, it starts sending discovery packets out. We also have to disable all the accelerations, because otherwise what sometimes the stack or the controller might do, if it's a real interface, it will try to coalesce multiple packets, like multiple CP packets, for example. And that's really good when you're running the application, but it's really bad when you're trying to test the switch. So those things need to be disabled. But that's basically what the script does. So now, how to start the model? It's the command line is relatively long, but it's easily understandable, and again, it's kind of embedded in the scripts that admin provides. So it also needs to be started as a super user, because we'll need to connect to the Linux kernel. So you specify the model name is called simple switch. That's just the executable. You specify the name of the JSON file that you want to be loaded, and log console enables the logging on the console, so you don't have to start the separate logger. And then what you can do, you can just bind even virtual Ethernet interfaces to the ports that are available in your switch. So in this case, I say switch port number 0 is bound to be 0. Switch port number 1 bound to be 2, and so on and so forth, as many as you want. And then the next thing you do, you just specify the thrift port. And that's again optional. By default, it starts on this port anyways, so that it can open the TCP connection to listen for the commands. And last thing, there's an additional parameter, --pcap, if you want. And in that case, it's going to get the packets from the files. So now the model is running. It can also save and load the packets into the pcap files. Now, what we need to do, we need to start our CLI. And again, it's just one thing is this CLI, I think, I don't know Anthony, if you did this in this latest version or not. Mm-hmm. It should be started from the directory, or it's in user local?
No, you need to leave it with us.
Okay, so yeah, so this one you'll need to go through the full path, so it's so a little more awkward, but that's where it is. And so that will start the CLI, and so then you can control your model. And of course, the most interesting part happens when you start injecting the traffic. So the one packet generator that we kind of supply and that we recommend is Scapy. Anyone knows? You guys use it? How many? Okay, I'll just put some examples. So basically, Scapy allows you to very easily form the packets, and I'll show you it on the next slide, a couple slides after that. So you can specify, for example, Ethernet header is being followed by IP header, by UDP, and so on. And there's a function called sendP, which allows you to send the packet out of the given interface. So obviously, Scapy needs to be run as root. And in terms of sniffing the packets, you can either use Wireshark, or you can, Scapy also has the function called sniff, and you can just tell it to sniff the packets. In terms of where you inject packets, it definitely makes sense to inject them on the peer port. When you sniff, it doesn't really matter. You can do it here, or you can do it here. Either port is fine, right? Because it should be the same thing. So, the CLI. So the CLI is a fairly simple thing. It's written in Python. It provides you the interactive shell, but also you can redirect standard input and just pump in your scripts. And that's very convenient, especially if you want to do something programmatic. You can, for example, use bash to dynamically create the script and pump each line into the CLI. The CLI is totally stateless, so it just executes the command and it doesn't really care much about the rest. So it contains generic commands for the P4 objects, and if there is a help, so you should be able to figure out how to do that. I'll just show you a couple of examples and you'll kind of do it. Here's kind of the latest dump of help that I got. So there are lots of commands to manipulate tables, and table indirect, those are the commands to deal with the tables which have action profiles. So you can see that you can do like get the information about the table, so it shows you what are the keys, what are the actions, and so on. You can dump a table, and so it will print you all the entries which exist in the table. There is obviously commands to add an entry, to modify an entry. There are commands to deal with counters, so you can read and reset those counters. There is a command to read and write register. So lots of good stuff, and obviously, you can type help, or you can do help and command name, and it prints you the syntax. So I'm not going to recycle that stuff here. Just wanted to show you a couple of things. So you say show tables, it shows you the list of tables that are defined in your P4 program. Then you can say table info, it shows table name and what are the keys, and then the actions, and for each action it shows the parameters of the action. So really nice. This was changed, so initially it was dump table, but I asked Anthony, and so now it's table dump. By the way, so it displays you the comments on the table, so you can see the key, and so these 3 ampersand signs, that's really useful in ternary match. So that's the value and that's the mask, and then it points to the action, what the action is chosen, and the parameters for the action. And so then there's a table add, so you can also specify the table name, action, the key, then this arrow, and the action data. So that you can kind of use for your reference. And then there are a couple of more interesting and more difficult commands that you might need to use if you want to do kind of the real L2 work, because the real L2 usually involves multicasting. So what the model has a fairly simple replication engine, where the multicast group is sort of consisting of nodes, and each node is defined by its replication ID and the list of ports which are in the node. So what you can do if you want to define a multicast group, effectively you need to create a group with a certain ID that you can choose on your own. Then you can create nodes, and for each node you specify the replication ID and the list of ports that should be in that node. And then you associate the node with the multicast group. And you can also associate the same node with other multicast groups if you have multiple of those. So, for example, if you send the packet out, and the metadata has the multicast group number 1, you will see that the model will send the packet to the egress pipeline multiple times. So once it will go, and the egress port will be number 1, and the replication ID will be 1. Second time it will be replication ID 1, egress port number 2, and so on and so forth, so that you can do the real thing.
And I think there is a bug, which I'm just seeing here. If For the port list, I think you should write them in increasing order. Otherwise,
No, that I just.
because the port map displayed here is incorrect. And now that I'm thinking about the code, I think they should.
I thought it was fine because I thought it was like 0, 1, 2, 3, 4, 5.
Yeah, exactly. 4 should be 1,
Yeah.
and 6
Maybe,
should be 1.
yeah.
Yeah. So it will
Okay,
work fine.
but
if
that's
they-
your bug.
Yeah, it's gonna work fine if you put them in increasing order.
Yeah, okay.
Yeah, I need to fix
Is anybody going to do Multicast related project? Then this is going to be the perfect one. But who uses Multicast? Nobody likes Multicast.
Well,
Switch vendors like it.
maybe multicast no, but you still need to have broadcast to be able to
Yeah.
do like the basic output.
Yeah.
So. That's actually one of the nice things about P4 that, when you have the program, right, it's always one packet on both sides, right? And all this magic we can upload to the traffic manager. Okay, so the other thing that also is important is, remember there was a question about the CPU port. So what we do here is we have a so-called mirror destinations. And so you can just choose that one of the mirror destinations will represent your CPU port. And so you can just associate a particular mirror destination, or what we say in this, it's called the clone spec. You can associate with a given VETH, and so that will be your CPU port. That's where the packets will go, so you can see that. Last thing I want to tell you is the Scapy syntax a little bit. So Scapy is also a very kind of popular free software which allows us to generate and to sniff packets, and it's easily extensible. So like in P4 you can define your own packet formats, you can do the same thing in Scapy. That's one of the beauties. And so here are some examples how you can define packets. So effectively it has those classes, and the division operation is overloaded to mean concatenation of different headers or encapsulation. So if you don't specify anything, then Scapy typically provides good defaults. But normally for my testing, I try to specify at least the basics. So you can specify here like Ethernet, source MAC address, destination MAC address, / .1q is obviously the VLAN tag. And what happens though is that once it sees that you're trying to use this scatter after this one, it will automatically set the ether type to BT100. When it says that you want to use IP after .1q, it will automatically set the ether type here to be 800 and so on. So once you have created the packet, you can take a look at it. So there are a couple of ways. So packet is an object, so it has two methods called show and show2. So in that case, it will kind of hierarchically display the packet very nicely with all the fields. The difference between show and show2 is show2 shows the real values for the calculated fields like checksums, and show doesn't do that. And then there's a hex dump function which prints the packet in regular hex format. That's what people use. And then there are basically two functions that you need to know. There's sendP, which takes the packets and sends it on a given interface. And you can like say I want to send 100 packets or whatever. And there's a function called sniff, which just listens on the interface, and every time the packet comes in, it calls the PRN function, so it could be a hex dump or a show, and prints it on the console, or does anything else you want to do with the packet.